Hey everyone, today's lesson is going to be on theoretical probability. Now, this theoretical probability is nothing new. You've actually been doing this the whole time, we just haven't called it theoretical probability. Theoretical probability still uses the exact same formula that you've been using throughout your probability unit. The formula is probability is equal to the total number of positive outcomes divided by the total number of outcomes. So let's have a quick refresher of theoretical probability and how to get the probability of certain events. Instead of picking a number on a dice or a heads or a tails on a coin, let's do something different. Let's pick a pillow at random. So what would the theoretical probability be of picking one of these cloud pillows at random? Well, the first thing we're going to have to do is find out how many pillows there are in total. There are 2, 4, 6, 8, 10, 12. So we know that there is 12 pillows in total. And how many cloud pillows are there? There's 1, 2, 3, 4, 5, 6, and 7. So there are 7 out of 12. So to write that, we would say the PR, and in brackets, cloud, so the probability of picking a cloud pillow would be 7 out of 12. What would the probability be of picking shark pillow? Well, we've only got one shark pillow over there. So we would write the probability of shark would be equal to 1 out of 12. So it's really important when you are writing probabilities that you do use the PR and then a word or a letter, depending on the situation of what you're trying to find, in order to tell us what that fraction actually means. Let's do one more. What's the probability of picking a bare face pillow? Well, you can see we have 1, 2 bare face pillows. So the probability of picking a bare face pillow would be 2 out of 12. Now if we have a look at that fraction, 2 over 12, there's a common factor there. And that common factor Now, if you have a look at that now, if we look, now if we have a look at this, now if we have a look at this fraction up here, you can see that there's a common factor. 2 fits into both 12 and 2. So we can simplify that fraction into 1 on 6. So we can see that 2 fits into 2 one time, and 2 fits into 12 6 times, so we can write it as 1 on 6. We're going to go to a different room now, and we're going to use probability to find out how many times something should happen. Now, it doesn't necessarily mean that it will happen that way, because it's all theoretical. It's what we think will happen. Let's head over to that room now. In this example, we're going to be looking at what's called a two-step experiment. So here we have a blue dice and a red dice. What we're going to do is we're going to roll one dice and then roll the other and see what combination we get and what those two dice add up to. Now this dice here, that has a total of 6 different outcomes because there is 6 sides on the dice. This red dice also has a total of 6 outcomes. So when we roll the two together, there's actually going to be a total of 36 outcomes because we can just multiply the outcomes of each individual event and find the total. Now, there's something to keep in mind when we're doing probability is that this blue dice is completely different from this red dice. So this blue one and this red one are completely different. So if I change this blue dice to a 3, I have a red 1 and a blue 3. However, if I change this dice and I make that a 3 and I turn that back to a 1, we have a blue 1 and a red 3. This is completely different to what it was before because we have a blue 1 and a red 3 instead of a red 1 and a blue 3. Let's move over to a bit of a table. Alright, so let's find what the sum of two numbers. So if here I roll a 1 and I roll a... Right, so let's put some values into this table. So here I have a blue 1 and a red 6. So on my table, I've written my blue numbers up the top and my red numbers down the bottom. So here I got a blue 1 and a red 6. Now, 1 plus 6 is 7. So blue 1 and red 6 here, just 7. If I roll again, and I get some different numbers, I've got a 4 and a 3. So I have a blue 4 and a red 3, and 4 plus 3, 7. Now, I'm going to quickly speed this up and fill in the rest of the table. So one question you might be asked is, what is the theoretical probability of getting a 7? So let's write here. So P R for 7. So how many 7s are there? There's 1, 2, 3, 4, 5, 6. There's 6 out of 36 because there's 6 across and 6 down. So there's a total of 36 things in this table. Now, we can simplify that because a 6 goes into 6 and a 6 goes into 36. So 6 divided by 6 is 1, and 36 divided by 6 is just 6. So the probability of getting a 7 is 1 out of 6. Another question you might be asked is, what is the probability of getting a number greater than 10? Write that, PR greater than 10. So this doesn't include the number 10. We want numbers that are greater than 10. So that is the numbers 11 and 12. So the probability of getting a number greater than 10 would be 3 out of 36. There is a highest common factor of 3 because 3 fits into 3 and 3 fits into 36. So let's simplify that. So 3 divided by 3 is just 1. 36 divided by 3 is 12. So the odds of getting a number greater than 10 is 1 out of 12. So that's far less likely than getting a 7. And you can see that from both the fraction and on this chart. The probability of getting a number greater than 10 is 1 on 12. What this means is that if we roll the dice 12 times, we expect one of those results to be a number greater than 10. Now this number is useful because we can use this probability to find out how many times we expect something to happen. And we can do that using the following formula. The expected number of results, so how many we expect to happen, is equal to the probability times the number of trials, or the number of times we attempt it. So if we roll the dice, if we roll 36 times, the expected probability would be equal to 1 on 12 times 36. Now, this just simplifies down to, so 1 times 36 is 36 on 12, and 36 divided by 12, just 3. So we would expect 3 greater than 10 results to be rolled when we roll 36 times.